Okay. Thank you. Okay, so let's start our first lecture, our first online lecture, as actually the second one for me. Today, the first one was at the 9:30 for the first section. We'll do your first lecture now, and I hope you will like it, and I hope things will go smooth as I planned. Okay, so this is where we stopped at. That's the point where we stopped at. If you recall, we introduced the velocity selector. We said that the velocity selector is a device that you can tune your magnetic field, electric field, such that the charges that leaves you should be able to see the cursor of my mouse right here. So the charges that leaves this region will be having an equal and opposite forces, which means that they will not deflect neither up or down. So how do we do this? By equating the electric and magnetic force on that charge, which basically canceling the force on that charge, or the net force would be zero. That charge is going to continue all the way till it reaches the end of this region without deflecting up nor down. So this is the magnitude of the electric force. This is the magnitude of the magnetic force. By equating both of them, reworking the equation for the velocity, we get the velocity that basically gets me to the end without deflecting up or down. So this is the one of the devices of the mass spectrometry. This one selects the ones with the velocity that I want by tuning the electric field and the magnetic field. The charges that I get at the end should be having net zero force and basically will make it to the next region. As I said before, by tuning the electric and magnetic field, you should be able to get the velocity that you want for the charges that you are injecting in the mass spectrometry. Now, at the end of the frequency selector or the charge selectors here, those are the charges that will reach this point without deflecting up and down with this velocity. So this is the velocity that I have selected. This is the velocity that I have selected, and then it enters the second region of the mass spectrometer where I only have magnetic field. Now this magnetic field will be responsible for deflecting, will be responsible for generating the cyclotron motion. Remember here, I am having those charges coming perpendicular on the magnetic field. Having said that, this means there is no component of that velocity along the magnetic field, which means that all of them will be going into the cyclotron motion. Okay. Okay. So all of you will be going, all that will be going into the cyclotron motion. Okay, let me see. All muted. Okay. Okay. So now, once it enters the second part of the mass spectrometer, they will, as it says, see the cyclotron motion. This cyclotron motion is calculated from this equation that we have talked about before, mb over q b2. Those are the magnitudes. Those are the magnitudes, and then I can obtain or calculate the mass to charge ratio. The mass to charge ratio by recording the distance here, which defines the radius, knowing the electric field, knowing the magnetic field in the first region, knowing the magnetic field in the second region, I should be able to calculate to obtain the mass to charge ratio, which is the radius times the second magnetic field divided by the velocity. Now the velocity comes from the, as I said, the ratio of the electric field to the first magnetic field, and then putting everything together, I can get the ratio of the mass to the charge by recording this distance, knowing the values of the electric field, magnetic field, and the second magnetic field. Then I can obtain the mass to the charge ratio for my ions that I am bombarding. Okay. Yeah, please try to mute yourself, mute your microphone in case you forgot. I can also mute all from here. Okay. Okay. So back to our lectures, then we have this example we will be solving in order to understand how do we, okay, in order to solve for the radius of the cyclotron motion and the mass spectrometer. Okay, if you can take a picture of the example, because I will be switching now the screen to my notebook. An electron is accelerated, so we know the charge is accelerated through a potential difference of 500 volts. So this is the delta V, and then injected into a uniform magnetic field. Once in the field, it completes half a revolution of 2 nanoseconds. So if the half revolution is 2 nanoseconds, then the full revolution would be 4 nanoseconds. So this is half the period, if you recall. What is the radius of its motion in the field? Okay. So now I'll be switching to the notebook here to. Okay, so let's solve this problem. We have, as I said, an electron. So my charge as an electron, 19 Coulomb. My potential difference, delta V, is 500 volts. This is what I know. I don't know the magnetic field. I know the half of the revolution, which is half T equals to 2 nanoseconds, or T is 4 power minus 9 seconds. So that's what I know. I need to calculate the radius of the cyclotron motion. So where do we start from? We start from putting first the equation. Oh, of course you can. Of course, Mohammed. Of course you can. Okay. Okay. So our cyclotron equals to the mass, the velocity over QB. Right? So I have the mass for the electron. I have the charge for the electron. I need to calculate the velocity, and I also need to calculate the magnetic field. So in order to calculate the velocity, remember I can go to the conservation of energy by equating the kinetic energy to the electric potential energy, which is delta K equals to minus delta U. However, since I know the charge and I know the electric potential difference, then this equals to minus Q delta V. This is Kf minus Ki, and this equals to minus 1.602 minus 19 times 500. This one is starting assuming from the rest, accelerated from the rest, and this one is half mv squared equals to 1.602 minus 19 times 500, or V is square root of 1.602 power minus 19 times 500 divided by 0.5, if you recall the mass for the electron, minus 31 kilogram, which is V equals to 1.33 power 7 meter per second. So I found the velocity. Now I need to find the magnetic field. Where do I calculate the magnetic field from? If you recall the period equation, T equals to 2 pi m over QB. I know the period, I know the mass, I know the charge, I need B. So B equals to 2 pi m divided by QT. Yeah, that's the mass of the electron. If you recall, the mass for the electron approximated by 9.11 to the power minus 31 kilogram. Now, the magnetic field equals to 2 pi times 9.11 again, minus 31, divided by magnitude 1.602 power minus 19 times 4 power minus 9. The magnetic field is given as now 8.94 to the power minus 3 Tesla. So this is the magnetic field. Now, putting everything together, the R cyclotron equals to mv over qb. Now I have all what 41. Oh, the 4. This is the, we said, if you recall, half the period is 2 nanoseconds, which means the full period is 4 nanoseconds, right? If it takes the charge, 2 nanoseconds to go half. The parameter then multiplied by 2 becomes, this is the equation of the magnetic field. This is the relationship we have derived earlier for the period of the and the frequency of the charge going in cyclotron motion. So putting everything now together, our cyclotron is 9.11 10 to the power minus 31 times the velocity, which is 1.33 minus 7 divided by 1 minus 19 times 8.9 for 10 to the power minus 3. I reached the edge here. Then our cyclotron is 8.47 millimeter. So this was I would be recording on the machine, the distance from the where the charge has entered the magnetic field, the distance curling up, the distance would be 8.47 millimeter. Okay, so we finished lecture 11 slides. Now we're going to go to lecture 12. Okay. Okay. So now let's start slides number 12. For number 12, so far we have discussed the charge, the forces induced, the magnetic forces induced on a single charge going into a magnetic field. But what happens if I have plenty of charges? Yeah, you're right, Muhammad. Okay, so if I have plenty of charges going into a magnetic field, this can be done through having a wire that has a current going into the magnetic field. So let's see where did this one come from. This is the main equation for the magnetic force that we have talked about due to the magnetic field. Q V vector cross B vector. This is for single charge. Now, what happens if I have a wire that has n charges? Then I have to look at the volume for this wire, which is the length times the cross section of the wire that gives me the volume. If I have n charges in that wire, then the total number of the charges would be n times Al. This is the total number of the charges times the Q as the charges inside this wire. Now those charges, if I substitute instead of a Q, NQAL in this equation, then I have NQAL V vector cross B vector. Now recall that the current is defined as we have derived it before as NQAV, the velocity. So this is the current I is NQAV. Now, if I am to substitute NQAV with I, my equation will end up to be F equals to L I vector cross B vector. However, it's easier for me to use the current as the scalar and use the L as the displacement vector that represents the shape of my wire. So in this case, I will be swapping here the L and I, then F for charges or a current into a wire will be I L vector cross B vector. So it is easier to use the current as the scalar, since the current is will be the same in that wire, and then use the displacement vector that represents the shape of the wire as the vector. So here becomes F equals to I L vector cross B vector. Now this is the magnetic force for a special case where I have a uniform magnetic field. Now, what happens if I don't have a uniform magnetic field? In this case, the integration has to be used in order to calculate the net force on uh, a wire that has currents in. So in this case, this will be the differential dF vector equals to I dl vector cross B vector. This becomes the equation that we should be using later on. As you will see, when I don't have a uniform magnetic field, this uniform magnetic field can be due to different reasons: external magnetic field applied, different locations. Okay. So right now, this is the equation that we have introduced for the uniform magnetic field, that we will see an example later on how to apply that equation. Let's look at this question. This question will show you now how do you treat, how do you find the direction of the magnetic force due to a current in a wire in the existence of a magnetic field. So in this question, as you see, we have a voltage source here that is generating a current in this wire, steady current in this closed wire, and the loop is partially inserted into the magnetic field, into a uniform magnetic field. In what direction is the net magnetic force on the closed loop of the wire? So we need to calculate the net magnetic force applied on this loop. We can talk about the exams later on. Okay, so as you can see from this example, that the current direction would be going this way, and this way. So we have here three distinguished wires with the same current going through. Let's apply the right-hand rule using the same approach we did for the single charge. So zoom in or zoom out. Okay, so I'll show you. So assume that we're all now sitting and facing. I'm seeing the screen that you guys are seeing. Okay, so looking at the screen right now, I can see that the current is going up. So I'll let my my fingers point to the direction of the current, and the magnetic field is pointing out of the screen, right? Is pointing out of the screen. So in this case, I have to curl in that direction. So I will keep the direction of the fingers up. However, I will rotate it this way such that when I curl in the direction of the magnetic field. And then in this case, my thumb will be pointing toward the force. So the force applied on this side would be this way. Let me call this one F1. Now, if I go to the other wire that is here with the opposite direction of the current, definitely the direction of the force will be in the opposite direction because the current has flipped here. We can also show you that. So if I have my fingers pointing downward and I am curling toward the magnetic field, see, I'm curling toward the magnetic field, then the force will be in this direction. And in this case, F1 would be pointing in this direction. So this will be the same force, however, opposite and the direction, because the same amount of the length, if you look at the length here, equals to the length here. So the force would be the same, however, opposite. So the net force so far is 0. So what's left is the upper side of the loop. This is the one that's going to decide on the direction of the force. So let's look at this side of the loop. The current are going in this direction. So remember I have to curl in the direction of the magnetic field. So the magnetic field is pointing out of the screen. So I will rotate my hand such that when it curls, it will be curling in the direction of the magnetic field, and now the force would be pointing up. So the force on that wire will be pointing upward, as you can see here, and the answer would be A. That's correct. It is A. Any question before we move on? Is that clear? That's a current. This is the current, and we are talking about the current having the direction of the positive charges. So the current is always pointing in the direction of the positive charges. It's a current. Yes, but it is the opposite. So the current is assumed to be the directions of the positive charges, which is opposite of the directions of the electrons. So we have talked, we explained that before. We said that the electrons move in the opposite direction of the holes. So if I have an electron moving in this direction, this means I have a hole that has been emptied in this direction. So my current defines the direction of what assumed to be the opposite charges, which is the opposite of the electrons. Electrons moves from the negative electrode toward the positive electrode of the battery, right? Which means there will be positive holes, as if there will be a positive holes moving from the positive electrode of the battery toward the negative electrode of the battery. So that the current positive direction is assumed to be the opposite of the electron's flow. the current positive direction is assumed to be the opposite of the electron's flow. That's why we said if we have an electron moving from the left to the right, this means we have almost as if we have a positive charge that has moved from the right to the left, and the direction of the current is the direction in the opposite direction of the electron's flow. Exactly. Bilal, is this clear? Did I answer? Did you? So Bilal, did I answer your question? Yeah, but the current is not the direction of the negative charges. The current is opposite. The positive direction of the current is opposite to the directions of the electrons. Okay. Yes. Okay. So this is how we do it. Now, let's look at this question. In this question, I have the full loop put into the magnetic field, a uniform magnetic field. This loop has a width and a length. And as you can see, the magnetic field is entering into the screen, entering into your screen. And I have the current going counterclockwise. So if we apply the right-hand rule and we look at that, our fingers defines the direction of the current, and then our fingers has to curl toward the magnetic field, then I will be rotating it this way such that my fingers will curl toward the magnetic field, and the force for the upper wire here will be pointing downward. So let me call this one F1. Now what happens to this bottom wire? I have the current going in this direction, right? And I will be curling toward the magnetic field. Then my thumb is pointing upward again because I have the same length. This should be the same force. I'll give it as F1 as well. Now let me evaluate the right side. The right side, I have the current going up. However, I will be curling in this direction. So I rotate my palm this way. My hand now is curling toward entering the screen in the direction of the magnetic field. Then my force will be pointing inward as well. So here is my force. This is force will be equaling to that force, as you can see here, because now the current is in the opposite direction. I have same length, and the net force applied on this loop and in that location would be 0. Okay. Let's move now to this example. If you want to take a picture of this slide, since I'll be switching to my notebook here. Okay, so here we have a wire that has a length of 25 centimeter long, lies along the z-axis. So if I am to draw that, X, Y, and Z. Then I have my wire on the Z like this. It doesn't matter where is it. It is along the Z. I'm not sure, Prakrot. I'm not sure if I have the notes here. Those notes are not saved under name, so you can rely on the video that will be uploaded later on. But now let's go back to here. If I have my wire laid out here on the Z-axis, then with the length of L, that equals 25 centimeter, then I can say that this defines a vector L that equals 0.25, and positive, the current is going in this direction, right? Then I will say that this L defines a vector here in the K direction. Then if I put the equation for the magnetic force, that is I L vector cross B vector, then my L now is 0.25 K and my current is 9 ampere. 9 times 0.25, 2.25. So I have F equals to 9 times 0.25 K cross. The B components are given to me at Bx, which is minus 0.242. This is I. The Y is minus 0.985 J, and the Z is minus 0.336 K. So if I say F equals to 2.25, okay, and now distribute cross minus 0.242 I, then if I take this minus outside, then will be 2.25 K cross 0.985 J. Then again take the minus outside, 2.25 K cross 0.336 K. Okay, so in this case, I know that the K cross K is 0. Always remember that a unit vector cross itself is 0. So in order now to calculate the other two components, I will be relying also on this diagram that tells me here to calculate the resulting unit vector. So F equals to K cross I. So let me look at K cross I by itself. K cross I is J. Since I have a minus, then it becomes minus J. So I'll put minus J. I'll leave the calculations till the end. And then K cross J is minus I. I have here minus, then it becomes plus I. So now I put the numbers. 2.25 times 0.242 is 0.544, and 2.25 times 0.985 equals to 2.21. Okay, so now the final force would be 2.21 I minus 0.544 J. This is the force, and definitely this wire, if it's allowed to move, it will move. This K is the unit vector along the Z axis. So that's K hat. Okay, so this is the force induced on the wire. What is the magnitude? The magnitude is square root of 2.21 squared plus 0.544 squared, and the answer is 2.21, I guess. Two point two eight Newton. Okay. If it should move, if it's allowed to move, yes. If it's free to move, yeah. Okay, so this is how we calculate the magnetic force due to a current in the existence of an external magnetic field. Any questions so far? Questions? No questions. Okay. Yeah, so we still have some time. Okay, so here all of them will be the accumulative force on the whole section. Why? Because it's a straight line, and all that wire will be facing the same force in the same direction because the magnetic field is uniform. We can talk about the final exam later on. Probably we're heading toward an online exam. It will be an exam with electronic, I would say, control. We'll talk about that later. Yeah, yeah, that's correct. Okay, so yes, yes, yes. As I said before, the magnetic field is uniform. So every single section of this wire is going to examine the same force, same directions. And remember that the current is the same everywhere in this wire. And the if you discretize this wire into segments, all equal segments, those equal segments are going to face the same force. So the accumulative force would be the force that we have calculated. Yeah. Now let's go to this question: a straight wire of mass. This one is to try it on your own. That straight wire of a mass 15 gram and 2 meter long carries a current of 8 ampere. This wire is aligned horizontally with the current going from west to east. You want to support the wire against the gravity. So we have a gravitational force here using the weakest possible uniform external magnetic field. So the mass here is responsible for the gravitational force that is pushing this wire down. We need to apply a magnetic field such that we generate a magnetic force opposing the gravitational force. So the wire will be, you know, at least hanging in its location with the zero net force. So in this case, you know how to calculate the gravitational force. F equals to mg for the gravitational force, and then so if this wire was placed horizontally this way, I will give you the hint on how to solve it. You will have to go through it. It's not different of what we have done, very similar. So you have the FG going this way. Now, this wire is a 2 meter long, and carries a current going from the west to the east. I is 8 ampere. So what you need to do, so we have the gravitational force pointing downward. We have the current going from the west to the east. I equals to 8 ampere. You need to decide on the direction of the magnetic field such that the induced force is opposing the gravitational force. So if I am to look, I need the force. I know the current is going in this direction. I need the force to be pointing upward, right? So the direction of the magnetic field should be, this is the direction where I am curling my fingers in. So the direction of the magnetic field should be into the page. So we said that this is the wire, current, 8 ampere, gravitational force is pointing FG. We said we need the F B pointing upward, which means that the magnetic field should be pointing into the page, right? So this is how the magnetic field should be pointing. And then you need to calculate from FG here equals to MG, equals to mg, where g is the gravity and m is the mass that we have here. You can calculate the force and then equate this to the FB, where the FB here equals to I L cross B, where FB magnitude. So if this is L is perpendicular on B, so IL sine theta, theta is 90 degrees, then this one is ILB. So we have the current times the length of the wire times the magnetic field equals to the force that you are going to get from the gravitational force, and then you can calculate the magnetic field. I can post the solution for this one later on. I can post a solution for this question later on, but this is how you should be approaching it. Do you have any question before we end the session? Go ahead. That's a good question. I will be starting from Wednesday, probably hosting an office hours, 2 hours, Monday, Wednesday, exactly the same. I'll try to stick to the same schedule, so your life would not be, disturbed by the changes of a schedule that I, changed at the last moment. Tutorials are starting from today. I believe you have 2 sessions today, if I'm not mistaken. Yes, at 2:30, probably the first session. It will be about magnetic field and forces. Yes, yes, they will. Assignment number 3. Yes, I will post it soon. I will post it soon. Labs, the 2 labs will be canceled, will be replaced by tutorial sessions. We probably should be able to finish the quizzes, having to have 6 quizzes. So you're still missing 1 quiz. I hope we will be able to have 1 more quiz through online. Not today, not this week. No quizzes this week. Maybe next week or the week after. We'll see. Exactly the same way. The TAs will hold Zoom sessions for you. I'll send them an email to remind them to send you the invitation link. But yes, they are working. They are working. You're welcome. Okay, I'll see you on Wednesday. Yeah, they're working on hosting the tutorial sessions on Zoom as well. Okay, great. Okay, great. Okay, so the TA, yeah, the TAs will be sending you the invitation link very soon. Okay. Okay. You're welcome. Thank you so much for coming. Thank you, and we'll see you. Thank you. We'll see you on Wednesday. Thank you.